Hi, everybody. Today we are going to be talking about exponential functions, as you can see on screen now. Mostly going to be the graphs in this first video, and in our next video we will talk about exponential functions that model real-life scenarios and situations. To start with, I wanted to show you guys examples of different types of growth and decay graphs, and you can see those on screen now. In the first three graphs you can see on screen in this Desmos graph, you'll see that they are growth functions. They are the red, purple, and black functions on screen. They are really close to the x-axis on the left and then grow really fast as it goes to the right. The three functions that are on the bottom of these six, the blue, green, and orange functions, are really big y values on the left and then get smaller and smaller and smaller. So you'll see in these functions that all of them are kind of the general y equals b to the power of x. These are going to be known as parent functions of exponential functions. You've heard the word parent function before. We've talked about families of functions lots this year and in prior years. And this is 6 different examples of parent functions. So that kind of shows all the different functions that you can see. So generally speaking, if you think about an exponential model compared to a linear one that you learn more about in Math 1, you will be able to see all of these examples in these notes on screen now. So generally the equations are sometimes just y equals a number like whatever b is to the power of x. Or sometimes you might see this third equation where it is 5 times 2.7 to the power of x plus 1. Those are just some numbers put in the 5 and the plus 1 as transformations. As far as data goes, you'll see that the x values are going up by 1s from 0 to 4, but the y values are doubling. The equation that would apply for this graph is y equals 2 to the power of x. Whatever that base is, in this case a 2, that is what you are multiplying by each time in order to get to the next y value. Here you are doubling. This is different than the linear functions people are more familiar with, because linear functions are adding by the same amount. These functions are multiplying by the same amount. We have an example of that y equals 2 to the x graph and y equals 1/3 to the x graph, the blue and green graphs, showing the difference between growth and decay. And you notice that both of them, without a value in the front, they are sharing a y-intercept. And we know y-intercepts can be found no matter what by making x equal to 0. Sometimes you will see in these sorts of equations, a lot of times you'll see a y equals an a, the 5 here, times 2.7, and then raised to a power of x. Y equals a times b to the x is very common. So now we will move back to Desmos and erase our writing from earlier. So now we can go into some tables. We have 3 equations here, and part of what you will learn how to do here in Math 3 is graph these, and mostly using the aid of Desmos. And the easiest way to do that is by making these into tables. So we see we have a parent function f of x equals 2 to the x, and that is in black on screen here. So we can hit our settings button and change that to a table, and we can look at, well, what is going to happen to this graph as we go from -2 to 3. And you can see that our values on screen here in the graph, our y values are being doubled from 0.25 to 0.5 all the way up to 8. And you can see that I could draw little arrows here, and well, that's times 2, and that is times 2, and all of that kind of multiplies as you go, and you can see that happening in this graph. The difference between that and our other graphs here are going to be, if we make those into tables, we can see that the points have kind of moved over, and where we had -1 or -2 and 0.25, now we have -1 and 0.25. And we can kind of recognize that might be happening from that x minus 1 graph. And then if we change it in a sort of a different way and make our third equation into a table, we can find out this information. One other thing to help you to find these answers is by simply using your calculator to figure out where your graph is going to be at certain x values. If I wanted to find that out, I would do 2 to the power of 2 minus 1. And I can see that my answer is 3, just like it is in the table. So graphing using tables will be the main thing you guys will be doing, whether you're using Desmos or whether you're using your graphing calculators here in class. The final thing we're going to be covering in this presentation is how our transformations will be working in more detail and what other vocabulary might you need to be on the lookout for. And we want to kind of transfer back to our notes here for a quick second and take a look at these exponential graph notes right here. So we can see that we have domain and range, which we should all remember from prior units. And we're going to be looking to find those on our graphs in our examples in a second. We will also be looking for shifts to the left and right, otherwise known as translations. And we will also be looking at shifts up and down, which are also called translations. And we will look at those in the following examples. In this first example, we have no transformations at all, but we do have a 3 times 2 to the power of x. And we can see how we have a point of 0, 3 as our main y-intercept point here. So there are no transformations other than this 3 being a dilation. If we compare that to our red graph here and our point 4, 4, our -4 right here is going to mean a translation right 4. So we could even kind of draw this on our graph where it is moving right 4, right 4, and we're moving up 1. So we could go up 1. And that is what gives us our transformation from 0, 3 to 4, 4. Additionally, as we kind of look back at our notes real quick here, well, we know what kind of translations we had, but we need to figure out domain and range. The good thing with all of these graphs is that our domain is going to be all real numbers. And that is something you guys will like because that is the case for every single exponential function that you will come across. They all go from all the way left and then continue to the right no matter what. The range can be slightly more challenging for a problem like this. And we want to make sure that we are paying close attention to that, in that if we have this red graph, we can see at 1 right here, and I can even add in a little imaginary line here, y equals 1, and even make it a dotted line. So so that we can see it a little bit better. And we can see that our red graph is kind of leveling out at that black dotted line. And our graph is basically staying above that black dotted line, and we can zoom out and see that even closer if we wanted to here. And we will say that our range is y is going to have to be bigger than 1. Because our range is y is bigger than 1, well, that means that we have a horizontal asymptote along that black dotted line. And so we would say our horizontal asymptote is y equals 1. And it basically will finish there for that example. And we've seen that we have a right 4 up 1. We know that our domain is all real numbers. Our range is that y is greater than 1. And our horizontal asymptote is y is equal to 1. And that just means that our red graph is going to get really close to that black dotted line, but never actually able to cross it. In our next graph that we're going to be working on is h of x right here. And we can see it pop up on screen right now. And it has some similarities in that they are both going to be growth functions based on this 2 right here. That makes it a growth function underneath the x there. And we are going to be looking for the same exact things as just another example here. So if we wanted to think it first in the same order we did it last time, well, we would think about going right, left, up, down. So if we look at the +2 here, well, that means it's going to go left 2. And we're going to go down 2 based on that 2 on the end here. Next, we might think about our domain and range. So our domain, like before, well, that's all real numbers. All reals. We'll abbreviate it a little bit this time. All reals. So our range is a little bit different because we can maybe put one of those imaginary lines in again. So if we type in y equals -2, which you'll notice is the same number as this n number in our equation, and we can make it a nice dotted line, make it orange. We can kind of see that, well, that our graph is going to level out at that line at -2. So we could say, and we can write it here on screen, that our range, in this case, it's going to be y is going to be less than -2. Our graph is upside down now. Y is less than -2. And our horizontal asymptote is going to be at y equals -2. We're not going to quite get there. We're going to level off at -2. And that covers all the graphing of exponential functions that you will need to know for this chapter, chapter 5, which is going to be entitled Exponential Functions and Logarithms. In our next video, we will cover exponential functions as they apply to the real world and look at some exponential growth and decay word problems that you may recognize from some prior years in Math 1 that you've covered this. So this will be mostly review for many of you guys. All of the graphs that I used in this presentation will be available to you guys on our Google Classroom page within one assignment. You all also will have some Delta Math assignments to complete based on this information on exponential graphs, as well as the following exponential word problems that you'll see in the next video. So I will see you all in that video. Goodbye for now.